Hi, today we're going to be talking about the CR circuit and its different responses. The circuit looks like this. Now, if you see very closely, it's pretty much the same circuit as we had before, but now we've switched the places for the capacitor and the resistor. Now, that really doesn't change anything because the current is the same in both elements, and therefore the voltage in both elements is also the same. So it's basically the same circuit. However, I still find that this representation is useful because it allows me to be clear as to where we're taking the output, especially when you're measuring the circuit at the lab. We definitely need to put the ground of the oscilloscope probe on the ground of the voltage source. So it's useful to always have our element where we want to measure also grounded together with the ground of the voltage source. And that's why I like to put it this way. Now, as I mentioned before, it's basically the same circuit. So we already calculated the voltage in the capacitor, which is the same as before, so no change there. And now we can apply Kirchhoff's voltage law to calculate the voltage in the resistor, so that the voltage in the resistor is equal to the voltage in the, to the input voltage minus the voltage in the capacitor. Now, we calculated last time in the previous videos, we know that for the charging case, the voltage in the capacitor equals V in times 1 minus e to the minus t over tau. And for the discharge, Vc of t equals Vi times e to the minus t over tau. So now for each of the two cases, we just calculate applying Kirchhoff's voltage law, this equation, and we get for the charging case Vr of t equals Vi minus Vi times 1 minus e to the minus t over tau. So this becomes Vi minus Vi plus Vi times e to the minus t over tau. And that cancels out with that one. And we get that the voltage in the resistor there you go. Otra vez. Is equal to plus Vi times e to the minus t over tau. And in the discharge case, we have Vr of t equals my input voltage minus my capacitor voltage, which is Vi times e to the minus t over tau. However, remember that when we look at the discharge case, this voltage source is switched off. So actually, this input voltage from my circuit is 0, and the capacitor voltage stays like it was. So Vr of t equals minus Vi times e to the minus t over tau for the discharge case. And so we have this one for the discharge, and this one for the charge. Now, we can also calculate the current by applying Ohm's law, which says that the current in a resistor is the voltage across the resistor over its resistance. So, the current, R, the current that flows through R is equal, for the charging case, VI over R times e to the minus t over tau. And the current in the resistor for the discharge case is minus VI over R times e to the minus t over tau. Which, of course, because it's Ohm's law, and Ohm's law tells me that the voltage and the current are proportional to each other, and the constant of proportionality is the R that we have here. So, also, these two current equations are the same equations that we calculated for the other case, because, of course, it's the same circuit, and we have the same current in both cases. So how does this look like when we plot that? So now let's gonna make a nice plot. That's T. Actually, if we have here our input voltage, like this, as we can see from these equations, the voltage, obviously, the voltage in the resistor is proportional to the current, and we already had the current before. We know that the current looks like this. And the voltage in the resistor looks like this, but it has exactly the same shape, but instead of being in amperes, it's in volts. And here I would have VI over R in amperes for the current, but I only have VI times that for the voltage. So it's just the voltage will be, so if I have here my ampere, this is amperes, then I have here VI over R, and here I have minus VI over R for my current. And this is my voltage axis. And I plot my current, my voltage in the resistor. So if my voltage in my resistor would look exactly like this, but instead, I have here VI and minus VI. Now, when we look at the current, of course, when I switch on the circuit, the current flows in this direction. When I switch off the voltage source, this is basically short-circuited and my current goes in the other direction. It's obvious to see that the current is negative, but where's the negative voltage coming from? It's also from that, because the current is flowing in this direction suddenly, and at the beginning, because the capacitor is charged, so we would have here my charged capacitor in parallel with my resistor. So the current's going to flow in this direction like this. And at the beginning, look, they are connected in parallel, right? So the capacitor was charged to VI, and then I switch off the source, I get this. And when I measure this, this is the opposite as that, so therefore I get minus VI. And that's my minus VI that comes from here in my red curve. Minus VI when I switch the source. So as you can see, one very nice thing about this is that although we cannot measure the current on the on an element directly using an oscilloscope, we can measure how the voltage in the resistor with an oscilloscope, which is proportional to the current of the circuit. So measuring the voltage at the resistor gives us an idea of how the current looks like. So, yeah, in the next videos, we're going to be talking about the transfer function and the frequency response of this circuit. Thanks for watching.